Sorry, Catherine, can you hear me now? 80. Yes. Okay, very good. Sorry about that. Okay, let me move my screen over. So let's recap where we left off. We looked at some experiments last class. A very important experiment, the Stern-Gerlach experiment. Let me get rid of this. And let's just recap where we were. And what I want to do today is to begin to introduce the language that we talk about these experiments and these results. We're going to have a universal language, which we call quantum mechanics, that will allow us to talk about these results and do calculations and do predictions, right? We need to have some sort of theoretical foundation to understand these things. And what's really, really powerful about this, we're going to find very quickly, this is a very simple example. One of the simplest examples of this kind of behavior in quantum mechanics. But the tools that we'll learn how to talk about it are universally applicable. So when we get to more complicated systems, we can use the same rules, same ideas, and it works just fine.
I actually have a question about the Stern-Gerlach experiment.
Go ahead.
So what if you were going to do it with just one atom?
Just one atom.
Would it have the same results? Like,
well, if we have
goes
50% chance it would go up or 50% chance it would go down.
Right, but then would it stay up forever and then once observed the up?
Yes.
Okay.
They work exactly the same way. This theory applies in some sense regardless of the number of atoms. It works for n equals 1 all the way up to n equals a mole. Now, when I say that, it works for n equals a mole, you'll clearly understand that that's not true because we predicted that a different result for a macroscopic. So, right, we expected them to be like little marbles, magnetic marbles that just don't deflect at all, but they all deflect, right? So, but the idea that it turns out the reason why a stream of classical magnets, macroscopic magnet balls, don't do what the Stern-Gerlach experiment shows with atoms, has to do with the experiment itself and the preparation of the sample. It's a very, very careful thing. You could theoretically make a Stern-Gerlach experiment with macroscopic balls. In fact, I had to dig it up. I don't want to waste time, but there's a paper published last week doing an experiment like this. It's a slightly different experiment, which I'll either introduce to you today or next class, where the particle is a 400 atom atomic nanocluster about 100 nanometers, 50 nanometers wide. Right? That's pretty big. That's a macroscopic object. That's what we call, imagine a protein doing this. Right? Something that you think is a big, large macroscopic object, you can prepare them. Yes, it did.
The same?
Yes, it does. It works exactly the same way. Now, it's not a magnetic experiment, but it uses the same principle. All right. And I'm going to introduce that general principle to you today. Let's recap what we saw. I got a little distracted. So the idea is very simple. We've got an oven, a stream of silver atoms in the vacuum. We effectively think as a bullet stream. It's got some distribution, but the idea is we're going to pass it through a magnetic field that is slightly inhomogeneous, meaning that the magnetic field on average is pointing kind of directly along the axis of the tube, but there's some variance in intensity, how strong the magnetic field is, and the direction. Okay, so it's kind of messy. I have a picture of that down here. Right, you have this inhomogeneous field, and depending on the initial conditions of an atom, they might get deflected up, down, we don't know. And what we observe in these scenarios, what we predict that in these scenarios with normal magnets, that on average, it's just like a machine gun. They go straight, they land straight, they deflect none at all up and down. And as you make the field more inhomogeneous, less clean, the precision of your shot becomes less precise, right? You get a slightly more smudged out target. Right? But that's not what they see at all. What they see with silver atoms, in fact, I don't have it here. Oh, right there. What they see in silver atoms, in fact, is that the atoms deflect up or deflect down. There's zero deflection straight on, like you would expect. All the atoms either deflect up or deflect down at some maximal amount, which is the opposite of what you would expect. Right? And so Stern-Gerlach do some tests of this. Right? The first thing they do is to test to make sure that this deflection is a property of the atom and not a property of the experimental results. So what they do is they deflect their atoms along the z-axis, block the downward deflecting ones, and then process the upwards deflecting ones through another splitter. And what they find is that anything that was up deflecting continues to be up deflecting, and vice versa. Which means that the nature of the deflection itself is intrinsic to the atom. These atoms are up deflecting atoms in the same way that silver atoms have X number of electrons or a mass or a charge. It's an intrinsic property. But what they find, interestingly, is that that property is ephemeral, meaning that it can be manipulated. It's not fixed. And it's not fixed in some sense in some very, very strong way. In the sense that if you deflect things along the z-axis up and down, take the up deflecting atoms and then deflect them left and right along the x-axis, another deflector, all we do is take the z deflector and turn it 90 degrees and deflect them left and right. And what we find is that 50 of them deflect left and 50 deflect right. Right? So that means that up deflection, down deflection is a different property than left and right deflection. Right? It means is that up deflecting atoms can also 50-50 direct left or right. Right? So that the directions are also intrinsic and they're separate from each other. They don't seem to be correlated. The worst problem, though, is that it seems that the left and right deflection and the up and down deflection are not compatible with each other. They're separate properties that can't be defined simultaneously. And the proof of it is if you pull out the z plus deflecting, the up deflecting, and then pull the left or right deflecting ones out, x minus, let's call that left deflecting. So we pull out the first up deflecting, then left deflecting, and then we check the z deflecting of those left deflecting atoms, right? So we do z plus, x minus, and then we check the z direction. And they've, in some sense, lost all that z information. And now they go back to deflecting up and down 50-50 like they did before. So the x and the z properties are unique, independent properties of each other of the atoms, but they're not compatible. You can only know one at a time. You can either have an up deflecting or a left deflecting. You can't have them up and left. It's impossible. And then you say, okay, well, again, there's two conclusions that we can have from this observation. One is that, again, x and z are incompatible, simultaneously incompatible measurements or properties. You can either be up deflecting or down deflecting or left deflecting or right deflecting, but not both. Or what's happened is that something in the x box, the second box up there, where we deflect left and right, does something to the atoms that perturbs them. Right? In some sense, the x and z are compatible, but the act of the measurement itself, say the deflection, causes something in the atom for it to erase its information, like you wipe it, like it's an eraser. Okay. So that would mean then that this x box, it's the instrument itself, the x deflector, that's causing the change in the z deflection. It's not something about the properties themselves. It's a mistake in our experiment. The experiment is, in some sense, too traumatic. It affects the atoms too much. So what Stern and Gerlach do is it's not, again, I say Stern and Gerlach, they weren't the ones that do these experiments, but in the same vein as Stern and Gerlach. They said, well, what if we take that x deflector and undo it? So we pass it through the x deflector, which we're hypothesizing may be affecting our atom, and then we put it through a combiner, right? We split the streams, and then we recombine them. Okay, so the net, you could say that the net thing that we're doing is nothing. We're splitting a stream and then immediately recombining it. So effectively, we're acting with the identity element, right? We're taking the original stream and reproducing it. But if it's the actual instrument itself affecting the z deflection, some traumatic erasal of that information, then the 50-50 that we see at the end in the previous experiment should be conserved. Because it's the act of splitting I'm proposing is causing the z information to be erased. Right? It's the manipulation by you, the human being, that's causing this to be messed up. right? And so if that were true, the separator would still cause that regardless of the combination. Okay, so we go do the combining instead, and what do we see at the end? A different result. By combining then recombining, not making any measurement about the x or the z or anything, we just combine and recombine, or separate and recombine. We don't lose any z information. So what does that tell me? Well, that tells me that it's not the bx box, the left-right splitter, that's causing the z information to be depleted, to be erased, but rather it's the act of the measurement of the x direction itself. Because the key difference between the last experiment and the top one is in the top one, we make an observation about how it deflects left or right. We block the pluses and we pass the minuses. So even though we're not actually putting it on our detector, we are making a conscious choice at the bx box, I'll get to you in just a second, to block the plus deflecting atoms on the x-axis. That constitutes a detection, a measurement, because we're making a choice. And by making that choice, and then passing it through the z box, we lose our information. In the final one, we're not making any claims about what's passing through the x box. Anything can pass through there and immediately gets recombined. No measurement is occurring. So what's happening is that the act of measuring the x removes the z information. It's not the act of applying an x direction, it's the act of measuring it and making a determination about the x character. The moment you do that, all the z information disappears. So they're not incompatible in a general sense, in the sense that these atoms are left, right, up and down deflecting, but in terms of your measurement, in terms of what you can define yourself, saying that this atom has these properties, the z and the x are mutually exclusive from each other. You can only measure one end. Question.
So what if they did the last thing, and then in the middle of it, so they separate them left and right, and then they measure it, and then instead of blocking one side, they put them back together. Now the measurement was taken, but it wasn't like half of them were removed.
Great question.
They were all put back together. So
what Angie's saying is instead of recombining, we put a detector there and we look at the distribution. And then later we recombine them. So we make a measurement of the x in the middle, but we don't block anything. Is that what you're asking?
Yeah.
That also ruins the information.
Okay.
Here's the interesting thing, right? So we're trying to distinguish between the act of blocking a certain pathway and identifying what's passing through pathways. From the point of quantum mechanics, they're exactly the same destructive process. Anytime we make any determination about the x deflection in this case, whether that means blocking or detecting, we collapse the z information and it resets. Doesn't matter what we do. So that's kind of scary. But there's a lot of power in this. Something that we also will eventually learn, and the homework plays around with this a little bit, is that these are manipulable. Imagine that I have this distribution here, 100% Z plus. Later, and I have some chemical or physical process where I'm using these atoms to complete a task. It turns out that this distribution, I can convert to any other distribution I want. There is a Stern-Gerlach box in some sense, that allows me to transform any distribution and deflections into another one. So if I don't like everything plus, well, I can certainly feed it through an X box and then split it to plus minus along the Z. But it turns out that I can even make boxes that give me 90-10 or 75-25 or 9-99-1. I can in some sense make any combination of up and down deflecting that I want. And there's a manipulation for me to do. So it's very powerful. Even though it's limited in this sense, I can manipulate the state however I please. This is the entire basis of quantum computing. Quantum computing takes objects that deflect up and down and uses microwave instrumentation and electronics to manipulate those states into different deflecting states. That's how it does calculations. I'll try to explain that to you as we go through. As you can see, it's not clear how we can take this information of up and down and convert it into zeros and ones for binary. to do math or to do computer work. But in fact, you can, and that's how a quantum computer works. I want to show you that language today. And maybe once we understand that language and how we represent this in kind of a universal way, it might make it more obvious how we can use this as zeros and ones in a computer. Okay. Now, to the new stuff. But what we're going to talk about today, starting today, and it's going to take us a couple weeks to get through it, but every instance of this discussion I have examples to give. So we're going to kind of take a journey for a couple weeks. But we're going to learn the basics of quantum mechanics today, starting today. And we're going to start what's called the postulates of quantum mechanics. I want to talk about this word postulates for a second. Because last semester, I tried to avoid using these words, but in any thermal class, use them. It's the idea of laws of thermodynamics. So physics with Kevin Green and Lausky talked about Newton's laws or Maxwell's laws. We talk about the laws of physics and chemistry, right? And what do laws mean? Well, they're statements about the behavior of objects that we assume to be true. And the unique thing about, say, Newton's laws tells us exactly using our senses how a billiard ball here with a force applied to it ends up over there. Right? We can track the trajectory of that ball at any point in space and any time in space, right? Any point in time. Right? So it's very logical to use the word laws because we can observe directly every step of that motion. It's a representation of a reality that we can perceive with our eyes and our senses. Quantum mechanics, we don't have that luxury, right? Quantum mechanics, we're looking at things indirectly. We're not looking at singular atoms, we're looking at their behaviors in experiments, like the Stern-Gerlach. Right? We're talking about silver atoms, not as individual atoms, but the nature of their deflection in a magnetic field. Right? So these are properties that we're describing, not necessarily the true nature. In some sense, I have no idea what's happening to the atoms in between the boxes. All I know is they start somewhere and they end up somewhere. How they propagate from one box to the other, I have no concept of at the moment. They might not just be, atoms may not just be billiard balls moving through a tube. They may be waves. There may be some structure to what matter looks microscopic that does not appeal to your senses at all, which is 100% true by the way. I'll show you that we can't think about atoms necessarily as little billiard balls. That actually gets us into trouble. And so how do you describe physical laws for things that you can't physically observe directly? But that's kind of a frustrating problem. In fact, many early physicists and chemists around the rise of all of this in the early 20th century felt that way too. How the hell can you say anything about things you can't observe? It's a real philosophical problem. So what they make up is this. The idea is that we have a series of experiments with very clear objective results. Stern-Gerlach experiment sticks out like a sore thumb. Right? There's nothing ambiguous about its results. Right? So we need a framework for describing and predicting those results. Right? We're not describing how an object evolves from t = 0 to the final stage, though we could theoretically do that. What I just want is just some understanding, some framework for me to just start thinking about these operations and these procedures that we're doing and the results. Right? It's an interpretation of things that you're physically seeing. It's an interpretative set of statements. So postulates are things that we assume to be true, but they're not quite as strong as laws because we're just, in some sense, our assumption is much stronger than our knowledge. It's in some sense an assumed list of rules. Instead of postulates, we postulate that these are the rules of quantum mechanics. It's not that they are, it's not the 10 commandments from a burning bush. It's an interpretation by human beings of experimental results. So we use a weaker word for them, postulates. The fact of the matter is there's different sets of postulates that describe these experiments. You get the same results, but they describe them from different points of view. We're going to be learning, and so there's different philosophies, different sets of postulates that you can apply that give you consistent results, but different ways to think about things. The way we're going to be talking about it is, it was developed by a man named Max Born. It's called the Born interpretation. And it was an interpretation of the postulates basically approved by the world in the 1920s. There's this big conference in Denmark called the Solvay Conference. Everyone and their mother was there. The Curies were there. Einstein was there. Bohr was there. Hertz was there. Mach was there. Any famous white dude from the 1900s, or, and I say one woman because Marie Curie is about the only one. Anyone that you've ever heard of was there that was alive in the 1900s. And they had a conversation about these results. And they said, how the hell are we going to move forward as a community when we can't agree on the interpretation? So they said, well, we got to all sit down and find an interpretation that all works for us. And so they come up, Max Born presents this interpretation of his postulate. And about half the audience is really happy about them. And the other half want to kill Born. Einstein thinks he's nuts. But 50-50 is good enough. You can't do much better. We know that we're Americans. We have a government here. The best you can do is 50-50. Everyone's unhappy. And that's the way that the postulates are. There's going to be problems, things that don't make sense to you in your mind, because we have to make compromises. There are things in quantum mechanics that just don't make sense from a logical point of view in the macroscopic world. Things that just don't exist in this. And so we just have to make some. We just have to make some things. Make some assumptions. Make some compromises. Another way that we talk about these things, for instance. There's another quote from a man named Everett. The idea is what's called the many worlds interpretation. The idea is that when you have a choice in quantum mechanics, what we call a superposition, where say up or down, the idea is that when a particle moves through that position, there are two timelines that get created simultaneously. There's an up timeline and a down timeline. There's 50% chance of creating the up timeline, 50% chance of creating down timeline. And the observation that you observe is that random timeline that was chosen. Right? This is where that multiverse idea comes from. The idea is that every quantum mechanical decision leads to a branching pathway of different timelines. And the way to interpret the kind of strange probabilistic results we get is to think about it as choosing timelines randomly. Okay?
What if we wanted to choose them specifically?
Well, the point, well, see, that's the thing I don't like about the many worlds interpretation, is that it gives you a sense of delusions of grandeur. Mm-hmm. And I want to emphasize that we are otherwise powerless to the laws of randomness.
Because you can make a decision, but how the rest of the world will respond and react to it is still infinite.
Right. So here's an interesting. Right. So I don't want to get too lost in this because it's not a philosophy class. But we have to think about locality versus global. Right. Right. The claim is that you create this. Right. You're thinking the butterfly effect. Right. I make a tiny decision that causes the world to split this way, and what are the consequences way down the line?
Right, but it doesn't cause the world to split this way necessarily, but it causes the world to split in a certain amount of ways, like maybe like
that violates relativity. Can't do that. So it's very complex, right? So we need the important thing is we're chemists, right? We need a theory that's practical. This is not practical. Would you agree with that?
No, I think
right, it's okay. Well, we could talk about it. Yeah, it's practical in the sense it might be fun to think about, but it's not practical for experiments.
Oh, right.
Remember, we're interpreting experiments. We're chemists, so it's not very useful. So let's do something useful, right? So there's pros and cons to everything. The advantage of this is that it gives us a way to start calculating things, instead of talking about timelines for 3 hours, because that's the way it works. All right, so the first postulate is, there's about 5 or 6 of them. Some of them are more important than others. And the first one we're going to talk about is called the wave function. And the principle of superposition. All right, I'm going to tackle this slightly differently than the other section. So they're going to see this content, but they're going to see it next class. And you're going to see the content I gave them next class. I'm flipping things around. So what I want to talk about is this concept of a wave function. Right? The wave function is a central object in quantum mechanics that describes the object of the system that you're observing. So the idea is that every silver atom in our stream can be represented by a wave function. Each one has a wave function. right? It's not in the sense we should think about not that necessarily this idea of a wave as the atom is a wave. We'll have to think about that a little bit. But it's this object, this mathematical object that we can do math and computations on that represents the object and gives us realistic results back. Okay, so don't think necessarily the wave function is a physical picture of the atom, but rather it's a useful representation of its properties that allows us to calculate anything about it. Okay? Think of it as a name, a label in some sense. So an object that represents the atom. Okay, so let's set up what I call a wave function, what a wave function is from the point of view of our Stern-Gerlach experiment. All right, so let's consider the BZ splitting, right, up and down. Right, we can make a choice, right, because there's two different properties we saw, x left and right, and z up and down. And they're perpendicular, they're different than each other. They're completely what we call orthogonal, meaning that they're completely separate properties that don't correlate to each other at all. What we can find is that we can consider our atoms in terms of the x direction, it's left and right deflecting, or it's up and down. We can make a choice, but we can't do both at the same time. All right, I'll show you that. So let's just think about up down. Right, and what I'm going to do is define a function, or just an object, a mathematical object, that represents the up deflecting atoms and the down deflecting atoms. Okay, we'll give them a name, a mathematical object. Okay, so the up deflecting atoms right, we're going to use the label phi for these, which is a little circle with a line, diagonal line through it. And we'll call it phi plus for the plus deflecting. Right, and in this example, we're going to we only have two options, right? So the atoms can either be up deflecting or down deflecting. Right, there's no other options. Right, they can either be one or the other. So what we're going to use is a mathematical structure that you're probably familiar with. We probably don't spend a lot of time about that makes this very, very easy. We're going to use vectors.
Yay.
Right? We're not going to use vectors for the entire class, but for this purpose, vectors are really useful because there's only two results. There's up and there's down. And so any vector representing an atom in this context is just two numbers. Right? So what I'm going to call it is a vector. Right? This is a vector with components 1 and 0. All right, the idea is that I have this coordinate system. You can think of it as a coordinate system, right, where one of the coordinates is phi plus, and the other coordinate is phi minus. Right, so so phi minus is a vector pointing in this direction. Phi minus. And phi plus is a vector in this direction. Right, and you can kind of just, if you just blur your eyes and change the labels, right, I can just kind of think of this as y, and this is kind of like x, right? And so these are just vectors in xy space, okay? So these are the two kind of generic results we have, right? You can either be up deflecting or down deflecting. These colors are off, but in 0, 1, things like that, okay? So these are vectors that represent an up deflecting atom and a down deflecting. Okay? They're just ones and zeros. Okay? That's not very interesting. But what can I do with vectors? What are special about vectors? What can I do with them? If I have two vectors, what can I do? What's an operation that you can do on vectors? Yes, you can add them. You can't multiply them. What do we call multiplication for vectors? That's not it. There's another product.
Dot product?
Dot product. What does a dot product return?
Scalar?
Yes, it returns a number. So we can add vectors. When you add two vectors together, what do you get back? A vector, right? And then we have a dot product, which takes two vectors and returns a number. All right, we'll look at both of those operations in a second. They both play crucial roles in this math. The dot product and the addition. I know that doesn't seem that interesting, but let me follow this. Let's do an example, right? So there's our down. What my claim is that, and this is our position, our what we call the completeness postulate. I'll get into in a second. Is that any valid state of the atom, silver atom, is any combination of these two. I can take any combination of these two vectors and come up with a new atom, a new state. So so these are called these special states. So these are our generic states. So these generic states are called, right? We have a special term for them. They're called basis states. And any valid wave function of our silver atom of a system, it doesn't have to be just a silver atom, right? And a valid wave function we write with the letter psi, the Greek letter psi. Right? You're going to see psi a lot in this class. When you see psi, think wave function. We can write a wave function for this system as any addition of these two basis states. So I can write with two different numbers. We could call it we'll call it A1, that's just the number, times phi plus A2 times phi minus. Okay, and there's one limitation. Okay, so what this means is that I can have a system that's up deflecting, a system that's down deflecting, and any combination of up and down deflecting I choose. But there's a limitation. The limitation is that if we think about it, these vectors are length 1. They're unit vectors. And one of the requirements for a wave function is that the vector representing it, the state that you're interested in, is also length 1. Everything has length of 1. Why that is not clear yet, but it has a beautiful interpretation that I will explain to you. So this has a limitation, and the limitation is that A1 squared plus A2 squared is equal to 1. Okay? So the squares of the scalars on the outside have to equal 1. What this guarantees is that this function, this wave function, is also length 1. Okay? It's not immediately obvious why that is, but it's not too hard to show the math that if you start with two length 1 vectors, basis vectors, and then multiply them and add them together with scalars, where the sum of the squares of the scalars are equal to 1, then the length of the resultant vector is also 1. Okay, so if I go to this diagram up here of the coordinate system, there is, in some sense, let me draw like this. There is a circle of states that are perfectly acceptable for our wave function. Right? Any of these directions are perfectly acceptable states. Right? I could pick any direction, right? So what the hell does it mean for a particle to be something in between up and down deflecting, right? If it's some random angle, right? If it's pointing directly up in this coordinate system, it's down deflecting. If it's pointing straight on, it's up deflecting. So what does it mean to be halfway in between? Right? So what that means is what are the physical interpretations of these scalars? Right? This says this is down deflecting, this is up deflecting, and our generic state is some combination of the two. And so these numbers tell us something about that state. And this is where one of Born's key interpretation points come in. A really, really simple idea. I'm going to put it on the next page. So this is what's called Born's probability rule.
Is this a different postulate?
No, it's the same rule. All right. So let's imagine, right, we have a generic wave function, right, that's equal to some number C1 times some basis function phi1, C2 phi2, all the way to C sub n phi n. All right, imagine this is an n deflecting state instead of a 2 deflecting state. We could cut it at 2. We just want plus and minus, but it could be some arbitrary atom that deflects a million different directions. Right? Right. So this is what we call this is what's called a general wave function with the property that I wrote before, the constraint that the sum over the indices of the coefficients squared is equal to 1. And what Born says is that the interpretation of this is that the probability of observing result, sorry, let me write result here, phi I. Okay, so that maybe that's up deflecting, down deflecting, left deflecting, whatever it is the absolute value of this number squared. So this number tells you the probability of observing that result. What's that?
Oh, no, never mind. Sorry.
So that number tells you the probability of observing that result. Okay, so let's do a quick example. Let's make a 50-50 mixture of up and down. Okay, so we want a 50-50 mixture. Right? So that means that our wave function for this system is some number c times phi plus some number c, the same number c, phi minus, right? They have the same probability, so they have to have the same coefficient. Probability is the coefficient squared. Okay, and we know, therefore, that 2c squared, that's the sum of the coefficients. Or sorry, no, it's 2 times c squared. That gives me a 4. Is equal to 1. Right? We sum over the coefficients. That's c squared plus c squared. That's 2c squared by Sydney. It's equal to 1. Right? And so that means c is 1 over the square root of 2. Right? Simple as that. Okay? So the wave function 1 over the square root of 2, phi plus phi minus, is the wave function for a system that's 50-50, right? Because they're equally weighted, right? So this would lead to a result, right, with a deflection. If we prepared our system in this state, we would have a deflection up and a deflection down that are 50-50, right? And the valid representation of this state is this function right here, which we can write as 1 over the square root of 2 times the vector 1, 1. Right? The reason why it's 1, 1 is because this is 1, 0. This is 0, 1. When you add two vectors, you add the components. So it's 1, 1. Right? Square root of 2, 1, 1. Right? So if I go into my figure right here of the coordinate system, right, this is saying that we're halfway between phi up and phi down, and it's 45 degrees. Right? This is 1 over the square root of 2 phi plus phi minus. Okay, this is what I mean. So this in some sense, right, this is a very abstract coordinate system. It's not a space, but rather it's a really easy way to think about the results of a potential experiment. The idea is that the atoms, the silver atoms, they're all prepared the same way. They're going to exist somewhere on this circle, the results of that experiment. It's the only possible results. Now, here's something that's very interesting. The probability is the square of the coefficient. So what I could do is I could take this vector that's pointing at 45 degrees and rotate it by pi. That leads me to this other one that's in the bottom left quadrant. Right? What would that be? Well, that would be 1 over the square root of 2. I'll write it. Right? We're in the negative quadrants for both. Right? So this is minus 1 over the square root of 2. Phi plus phi minus. There's a negative sign there. If we put 1 over here, right, this would be 1 over the square root of 2 phi plus minus phi minus. And if I were to put 1 in the top left quadrant, right, that's 1 over the square root of 2 phi minus phi plus.
Dude, we have a whole unit circle now.
Now we have a whole unit circle. Let me ask you this. If I prepared one of those 4 sheets I drew, would the results of my deflection be any different between the 4? Would I see anything different? No, right? Because remember, the coefficients are the squares of the components, and you lose the minus sign. So there are 4 equivalent states that I can prepare that all give me the same result. Why is that important? Well, it's not clear why that's important yet, but it becomes very important. The idea, this turns out to be an essential quality of a quantum mechanical system, is that the results are in some sense independent of what we call the phase. We'll talk about phase a little more carefully. This is where waves start to come in. We'll do that next class, talk about waves. But the idea is that there are multiple states that all give the same results, and they're just different by signs. Right? From our point of view, which is just deflection, it doesn't make any difference one way or the other. They all give 50-50. Now here's the interesting. There's a possibility. You can think about this a little more difficult and a trickier scenario, and this turns out to work. Imagine that you create simultaneously 2 silver atoms at a time. Okay. And one of them is in the top right quadrant, right? So a plus is a symmetric combination. So one of them is in the plus combination. All right, let me go ahead and write these out as vectors. This is equal to 1 over the square root of 2, 1, 1. Right? And this is equal to 1 over the square root of 2, 1 minus 1, and so on and so forth. Imagine I create 2 silver atoms at the same time. Right? That are, one of them's in this state, and the other one's in this state. Okay? And I put them into a combiner. All right? The net result would be the sum of these 2 wave functions. A plus plus and a plus minus. Okay? So when I take these 2 streams and combine them, I take a plus plus and a plus minus together, and the net result is the sum of the 2. Everything is linear. They just add together. Vectors add together, right? That's all we do. So we have 2 experiments that are correlated. We combine them into one correlated experiment, and so we add the results together. So what happens? Well, the plus combinations add together. You get 1 plus 1, and then we have to renormalize, so because that's be length 1, but it's still 1. What happens to the other component? 1 minus 1, it goes to 0. What would happen? What does that mean? That means that if we take a stream of atoms that are combined plus plus, and a stream of atoms that are combined plus minus, and then combine them together, we lose all the minus states. We are left with a result that's 1, 0. They're all up deflecting. They interfere with each other and cancel themselves out. So we can manipulate these systems. Let me write that down just to repeat that. Okay, let's just work through that math really quickly. So imagine we have a box, right, that takes in 1, 1. I'm just going to get rid of the 1 over the square root of 2 just to keep it simple. You're going to see me negate that. It's of course important, but we can always normalize at the end. And we just got to make sure that the end result is length 1. So we feed in 1, 1 and 1, 0 there. And we combine them. So we call this phi 1 and this phi 2. And the result, of course, is phi 1 plus phi 2, right? Which is equal to 1, 1 plus 1 minus 1, which once I normalize, it's going to be 2, 0, but it has to be length 1, is equivalent to 1, 0, right? Which is phi plus, right? That's up deflecting. Okay, so what we would see out of this box are only Z plus atoms only. Right? What's the distribution of Z plus and Z minus going in? It's 50-50. Right? We have 50% up here, 50% down here, 50% up here, 50% down here. They're combining, and then we're left with only Z up. Because the phase of the minus contribution, the second component, are opposite each other. They have opposite phases. They're on 180 degrees. They're 180 degrees away on the circle. And so when they add together, they interfere and destroy each other. And so you only get Z atoms, Z plus atoms, right? We literally manipulate the system and cancel out the down deflecting component by providing two streams of 50-50s, but with different phases, different angles, different directions, however you want to think about it. Phase is the right term. We haven't talked about waves yet, but you can kind of get the idea, right? Vectors are really useful for this. So you can imagine there's a box that we can apply for any vector. We can take any vector that we start with and move it to any other position. There's always an operation that takes me from one to the other. I should be able to convince you of that because these vectors lie on a circle. Very easy to take a line on a circle and rotate it at some degrees. There's a transformation that allows you to do that rotation. Right? So there's a box that will allow you to take any angle vector and rotate it by any angle you want to get some other state. Right? This is quantum computing. There are things in quantum computing called gates. You can combine gates to do logic operations and or not, the key operations of computation. And by combining these rotations, you can generate arbitrary states. And so if you assign specific states to specific information, say 1, 0 is a 1 and 0, 1 is a 0, I can always check if it's a 1 or a 0, and I can convert a 1 to a 0 if I want. I can compare two 1s. I can compare a 1 versus 0. There's lots of different things I can do. And so I can build a computer with just these two, with just silver atoms. Right? Practically, it's very hard to do that. But there's nothing stopping me from using silver atoms and representing their deflections as 0s and 1s and recreating all of computation from this process. It's very, very powerful. Okay, so let's stop for a second. There's two things I want to think about today. One of them we'll come back to. One is that idea of a transformation, right? What if we want to do something? We have an up deflecting atom, and we want to convert it into a down deflecting atom, or some operation. What does the object look like for that operation? In some sense, if the particles are vectors, represent the atoms as vectors, what are the Stern-Gerlach boxes? How do we represent the box, the observation and manipulation itself as a mathematical object? Because we're using a box and doing something to these atoms. So we have to introduce that concept of the operation that we do on these atoms with an object that we call an operator. Right? So we'll come back to the operators in a couple of lectures. Right? So there's that object, right? We need a mathematical object that takes one vector and turns it into another one. Okay, we've already looked at an example. Taking plus minus and plus plus converting into just up deflecting. That's a box. There's a box that we can create. So if we can come up with the language to talk about these boxes, we can devise any box we want to manipulate any object into another one. Okay? The other thing that we have to consider is this problem that we just observed here, that where I took particles, atoms, and somehow I've changed their properties by adding and subtracting atoms together in strings. So a little strange, right? And so we need to understand this math a little. The other math that we don't really quite understand either is the fact that when we do z, we define things on z, and then when we do x, we lose all the z information. Right? So we have to understand that as well. That's going to take us a little bit to get to, but there's an answer to that problem. And then we have this issue of things canceling each other out due to phase. These are correlated issues. These two things, they're two different issues, but they are correlated and the answer is the same. Let's tackle the phase issue. Let's start that. Right? How can I do this with physical objects and I can get them to cancel each other out in their properties? How does that work? Well, I'm going to tell you guys, who here has AirPods? All right, you guys know that. Do you guys know how active noise canceling works in an AirPod? Someone want to explain it to me? Matt, Sydney.
In short, it's essentially doing the inverse space.
Right.
So it's for them, does it 2600 hertz? It generates inside your ear about 2600 hertz.
Correct.
180 degrees.
Correct.
Phase. Sorry.
Exactly. So it uses phase cancellation, uses destructive interference to remove signals. So the idea is this.
Is that your ear
So here,
with the AirPod in it?
this is my AirPod. Okay, and on the outside, there's some noise, all right? And he's talking to me.
Blah, blah,
Blah, blah, blah, blah, blah, right? And it's coming in like that, all right? It's got some frequency and some phase. What does phase? Remember, frequency tells you something about the wavelength. Phase tells you at what point in the wave happens at t equals 0. Okay, so that's a sine wave. If I move it 90 degrees, it would start at the peak of the wave. That would be in a phase of 90 degrees, and it would be a cosine. You guys remember this? Sine omega t plus phi, right? So phi is the phase, right? And so how does the AirPod cancel this out? Well, the AirPod generates a signal inside your ear that is 180 degrees out of phase. So it goes like this. This is the AirPod signal. And this is the noise outside. This is the angiometry. And then what happens when we add these together, right? We can destructively interfere. The negatives add to the positives, and the positive adds to the negative, right? And the result is, right, something that looks basically like noise. Right? We cancel everything out. That's destructive interference. Does that remind you at all about this concept that we just had here? Right? What have we done here? We've taken something that has an angle on a circle. It's got some phase. It's pointing at 45 degrees. It's got 45 degrees phase, right? And then we add to it another particle, another stream of particles that has phase of 45 plus 180, like 210, 20, or whatever it is. I don't know what it is. Right? And then what happens when we add those two waves out of phase? They cancel out. They destructively interfere. And what are we left with? A resultant wave that negates all of the down deflecting and only leaves the up deflecting. The up deflecting part of the wave is constructively interfering with itself. And then the down deflecting part of this wave, as we call it, is destructively interfering with itself. It's exactly the same process as active noise canceling. We're just noise canceling out the down deflecting atoms by adding a stream of opposite phase. All right, does anyone, so this is called interference. The sum of two waves is called interference. But it's also called the idea that of what's called the principle. Let me bring. So I feel bad for Katie. She's on here and I'm talking on the board. Right. The idea is that waves have the principle of superposition. Right. The idea is that any wave any two waves added together is also a wave. Right? Right? Particles, rather, I should say all quantum mechanical objects, have phase like a wave and can be added or subtracted in a superposition. Right? So what does that mean? Right? So if you have one stream of silver atoms, right, that has wave function 1, and you have another stream, wave function 2, that go into a box and combine, right? We can either combine with a plus or a minus. It doesn't matter. We can do either one. Right? We get the plus combination. That's going to be phi 1 plus phi 2. We can also get the minus combination, which is phi 1 minus phi 2. There's other combinations of negative signs as well, but we'll just do these for now. And these are also valid states, valid wave functions for our system. We could just add them together. So we have two different states, two different streams of atoms that are correlated. We put them together into one state. The next state is the sum or the difference of those two states. This is, we're going to find this is so powerful, and it's why quantum mechanics, I say, is easy compared to Newtonian physics. This is what's called linearity. Wave functions, states of molecules or atoms, the things that we represent molecules and atoms are linear. What does it mean to be linear?
Wait, so it's kind of like saying that if you added, like, if you had a mixture of 50-50 and then you took out, you separated them, and then maybe like you added in like 75% of the ups and 25% of the downs together, and then see, like, that's a different
It's a different
wave
state.
function.
And that's yes.
Okay.
Yes.
Okay,
Correct.
got you.
Yes. That would just so what you're
But it would still end up on that.
what you're describing is you're taking two streams of atoms, and then when you add the vectors together, it leads to a net vector that gives you that distribution that you want.
Okay.
Yes, that's exactly. And that's exactly what I mean by that.
So there's no way to add any amount of atoms together of different proportions that it would give you anywhere off of that circle.
Correct.
Okay, gotcha.
Correct. But this circle constitutes every possible combination of atoms with probability 1.
Right.
It's every number.
Okay, gotcha.
It's a circle had so that this is a very obscure math point, but the countability of the number, the amount of points on a circle is the same number of points of real numbers. So there's equal. So if you instead took this and stretched it, you could convert this to something that's on a real number line and get the same amount of information.
Right. Yeah.
It just doesn't have that circularity that we want. As we'll see that the fact that it's on a circle is extremely important. We'll see that. I haven't quite gotten to the reason why the circle here is here. But there's an important factor that we're going to see why the circle is very useful. All right, so wave functions are linear. It means that when we add them together, we get a new one out. That's basically what it means. Basically, linear things have two operations. One is that if you multiply two wave functions together by a number, the number distributes. Right? And that they're let me get the right formula for this. Hold on. Like,
And psi is also a vector, right? Or is psi?
it is. Yeah, they're all vectors. So let me erase this one. This is not the right one. Oh yeah, sorry. And the other one is that if psi is a function of a variable and that variable is multiplied by a number, so like x, the a can be removed, right? So this is some variable. We'll talk about variables later, but we're going to see that wave functions, they can be. The idea is that if psi is a vector, there can always, if all the components are multiplied by a constant, you can factor the constant out. That's all that means. And this says that when you add two vectors together and multiply them by a scalar, the normal linear math works that you have for numbers. Okay, that's what that means. This is extremely powerful. Let me tell you why. It's not obvious why. Because vectors are just kind of boring objects. There's a reason why it's so cool that we can use vectors here. You can use vectors to think about the position and the trajectory of objects in Newton's laws. Like billiard balls, you can draw a vector on them and you know where the velocity is, right? So you can kind of get a sense about something, but that vector isn't really an intrinsic property of the atom. It's just some directional information about the atom and the coordinates of the atom. And so the vector is just a representation of the position and the momentum of the atom. The wave function here, this vector is the atom itself in some sense. It's something representing the atom as a body, not its position and its but itself, right? It represents the object itself. And objects in Newton's laws are not linear. There's a very simple proof to this. Anyone read Three-Body Problem or see the Netflix show? What do we learn about the three-body problem?
I've been right in the middle of the book, so.
You should know already because you've probably already been in a video game.
Yeah.
What's the goal of the video game in Three-Body Problem?
They're trying to figure out how the three suns rotate around.
Right. So in Three-Body Problem, it's a science fiction book written by the Chinese. It's a very interesting, poorly written but very interesting book. There's this video game that's like sent to Earth or something like that. This big conspiracy from the aliens thing. It's a crazy story. But the goal of the game is you're placed on this imaginary planet, and you're like the god of this planet, and your goal is to basically figure out the moon, Earth, sun, the sun cycle of this planet that has three suns. Or is it two suns? Three suns. Three suns. And so you have a body and three suns that are orbiting. And so the entire period, so the goal is
the suns are orbiting.
Or sorry, the moon, the sun, well, the suns are orbiting each other, and you've got this planet. And the goal is for you to develop a civilization that lasts long enough to be able to figure out and predict the pattern of the suns. Because there are certain situations where the suns are so close that it melts everybody or it freezes the Earth. Because what you learn in physics is if you have two objects orbiting each other, right? Say the sun and the Earth, that's a stable orbit, right? We can define the center of mass, what they call the barycenter, and you get the nice simple rotational physics of two objects. You should have learned that in physics 1. The moment you add another object, third body, a planet, let's say two planets of equal size that are close together in the sun. The moment you do that, you can't solve Newton's laws anymore. Because Newton's laws are nonlinear. What that means is that the physics of one body is different than the physics of two bodies, which are different than the physics of three bodies. They don't add together.
Tell me there's like a movie adaptation.
There is. There's a Netflix TV show called Three-Body Problem.
Okay.
I think it came out last year. It's good. It's not bad. Don't watch the Chinese one. It's really bad. And so the goal is for the player in this game to come up with a model to be able to determine the orbits of these suns, right, in this 4-body system. And I don't think anyone ever figures it out, right? Now, eventually they get far enough, I think the game eventually win. But what you realize is that you can't do it because it turns out that a 3-body system in Newtonian physics and planetary orbits, whatever, is not stable. There are basically, the number of stable solutions, 3 bodies is basically negligible. It's almost impossible to get 3 bodies to orbit each other stably.
I already have a solution for it.
No, you don't.
Yeah, I do.
And so that's a problem, right? That really sucks because obviously we can watch the physics of one billiard ball. That's no problem. It's easy to look at the orbit, two billiard balls orbiting each other. In fact, we'll do that math in this class. But the moment you bring in three bodies, all hell breaks loose. You can't solve Newton's laws. Not every solution is stable. Most solutions are not stable. Most of them cause all the suns and moons to bounce off each other and fly away. Right? It's very hard to make a bound orbit of three objects. Quantum mechanics, it's trivial. If you know the physics of one object, by linearity, you know the physics of two objects. Because each object has a wave function, and we can add them together, and that's the state of the two-object system. Now, what if we have three objects? Well, I'll just add psi 3 there. If we have four objects, I'll add another wave function. And I can keep adding the wave functions over and over and over again. I can have it in many wave functions as I want, arbitrary number. The physics have not changed because the physics are linear. The physics of one object is the same as the physics of two objects, which is the same as the physics of three objects. The only difference is that they're multiplied by some number. That's really powerful because eventually we're going to get to a multi-body orbit problem. It's called a proton and two electrons. It's the helium atom. It's a nucleus and two electrons. There we have to come up with a stable orbit of a nucleus and multiple electrons. If we're up to Newton, Newton would say, yeah, right, I can do that. Newton could never figure it out because his solutions don't work in that scenario. But wave functions do. And I can pull up the computer right now and solve for the wave function of the helium atom that's perfectly stable, gives me all the energies, all the spectra, all the properties of helium perfectly accurately. Because the theory that I use is linear. It allows us to solve for chemistry. If we understand the hydrogen atom, we can understand the helium atom. Then we can understand the lithium atom, and the carbon atom, the boron atom, and the oxygen atom. Go all the way down to uranium and plutonium. Of course, it gets more complicated. You got more bodies on the The energies get higher, and we'll see all that. But the fact of the matter is that the solution is always possible. This is why chemistry is so flexible and so scalable, is that the theory that works for tiny little objects like hydrogen work for big things too. And that's why us chemists sit around thinking about hydrogen and helium and all these boring atoms. They're not boring. Because if you understand hydrogen perfectly, you understand the entire periodic table perfectly. Because it's scalable, it expands, it's linear. And that you don't have that luxury in classical physics. All right, that's what makes this a little easier, gives us a little bit of help. Because it allows us to take very simple problems that are very easy to understand and then kind of have a sustainable contingency plan and exit strategy for us to expand it to more complicated issues. And that's the way that this class is going to work. We're going to start with simple problems and then make them more complicated and realize that we just have to use linearity. The math might be slightly more complicated, we have more moving things. But the principles are exactly the same because the principles for one object are the same for n objects. Right? You can't say that about billiard balls. You absolutely cannot say that about billiard balls. Okay, so that was my spiel about wave functions. So wave function is a vector. Right? Later we're going to, you can imagine there are some things that aren't very convenient to use vectors for. Like, what is a vector that represents a molecule? It turns out you can write a vector that represents a molecule. Right? But it's not always the most convenient way to think about things. Because what we really want to think about, in some sense, right, imagine that we want to do an experiment where we want to measure the structure of a quantum mechanical body, like a molecule. We want to know the bond lengths and the bond anchors. It's not going to be really useful to think about vectors. We're going to think about atoms in space, electrons in space. So we're going to have X and Y and Z coordinates. We have some space. It's not just up and down deflections, right? There's a continuum of points where electrons can exist and spaces where atoms, nuclei sit, right? Like bond lengths and things. Right? And so using these vectors may not be all that appropriate. We might want to go into a spatial representation of things. If you're doing things like crystals, or you're looking at semiconductors, solar cells, things where energy plays a big role, motion of electrons across band gaps, like in a semiconductor. Their position doesn't make a lot of sense either. So there might be a different representation for the wave functions where position doesn't work and these vectors are very awkward. We might want to think about the momenta or the motion of the electrons, the energy of the electrons. So there's different ways that we can represent the vectors or these wave functions. We can think about them in terms of their deflections. We can think about them in terms of the positions of the atoms. We can think about them in terms of the momentum of the atoms, their mass and their velocities. And it turns out that we can choose whichever representation is appropriate for our experiment. In this experiment, up and down deflecting works great for us. Vectors are really simple. As we'll see, gives us all the math that we need once we get through all the math. But when we get to helium or we get to the hydrochloric acid molecule, it's not going to be useful to think about vectors of HCl. How do you even represent a vector for HCl? But it might be useful to think about where the electrons are in space around the nuclei. That means that the wave function of those wave functions of those electrons have a spatial quality to them. It's going to be about the probability of finding the electron at a certain position. It's the same concept of finding a silver atom deflecting up or deflecting down. We can also make the same argument and say, well, we can maybe do an experiment where we ask where the electrons in a molecule are. Once we know that, we can find the bonds. So that's where the electrons are, the bonds. Right? So that will allow us to introduce a wave function of position, psi of x, that tells us something about the probability of finding an electron at position x in the. Or maybe the probability of finding an electron in a semiconductor of some velocity. We'll have some measurement of that. Maybe there's some 50% chance that we find an electron in this point. The wave function will tell us that. So we have to find some way to take these wave functions, these vectors, and to project them into a continuous space, like position or momentum. We want to think about electrons and where they sit in a molecule. We can't do this in fact. Right, so we're going to have to come up with ways to convert from these vectors into representations of space or momentum or energy, things that are convenient for our experiments. It just depends on the experiment. Every time we choose a set of base states, the base states are influenced by the experiment we want to do. It's not useful to think about deflection when we're doing structure. It's also not useful to think about structure and position when you're doing deflection. So we have to have different representations of the wave functions that are contextualized based on the experiment we're doing. All right, and in chemistry, position is important because we care about structure. We want to care about where electrons are in a molecule. That tells us the structure of the bond. So we're going to have to figure out how does this math tie into space. Right? About finding things in a region. What's the chance of finding an electron at this point? Right? We're going to have to think about X and Y and Z there, positionally. So we have to find some way to take this information and convert it into space. We'll be able to do that. It takes a little bit of work. But what we'll be able to do is to move away from vectors and move into something that's a function of X instead. Just some sign, as we'll see, it's just sines and cosines. We'll have sines and cosines of it. Right? We'll come back to that. All right, so next class, we'll talk about position and momentum and converting from these vectors into a new space that allow us to do more chemistry. All right, have a good one, guys.
Can I tell you how I solved this?
Yeah, go ahead.
I would build a ship and fly somewhere else.
Oh, yeah, just leave?
Boom, problem solved.
Well, you have to be careful with that because you have to have enough escape velocity to get past the sun.
Right.
That under in a wrong situation, you might be gravitational trap.
We just have to figure out how big the suns are.
It's tricky.
Thank you.
Thank you, you too.
Or I was also thinking like build one shelter for when it's too hot and build one shelter